Now, as promised in the previous session, I'll give you a few more polar plots. They are the square of the modulus of spherical harmonics. Okay. This one for L is 3, M equals 0. I don't have the mathematical formula for that written up, but well, yeah, just take it on trust. So look what's happening. You're getting these sort of mini lobes now, but two sets of them, like figure of 8 that way and a figure of 8 that way, or if you like a mini 4-leaf clover in the middle here, and two larger lobes. And for L is 3, M is plus 1. You get sort of like a larger 4-leaf clover and two smaller lobes of this kind. And for L3, M2, you get sort of 4-leaf clover again. And for L is 3, M is 3, you get a simpler shape. And that seems to be a pattern, in fact, because it was the same for L is 2, M is 2, and for L is 1, M is 1. You got this sort of figure of 8, horizontal figure of 8 in all three cases. Okay, and well, I've mentioned this before, but good for a bit of revision. What are these polar plots? What are they? They are the square of the modulus of your spherical harmonics. And what are spherical harmonics? They are eigenfunctions of L squared operator and the z component of L, the AngularMmntm operator. So they give you the probability distribution of finding the electron at a given angle, theta and phi, in this case theta, from the nucleus. Right? So these are probability distribution. So in other words, at these positions, this particular angle theta, right? Maybe it's these are plots of the angle theta. So the electron then is much more likely to be in this lobe than it is, say, here. Here, probably 0. Okay. So the electron's more likely to be in these four angles four values of theta, the angle, than say here or here or here or here. The probability at 0, theta 0 or 90 degrees or 180 degrees, 0. So they give you the probability, the highest probabilities of finding the electron at those angles, theta. Okay. So and you notice that as L and M get higher, the shape of these probability distributions, these polar plots, gets more complicated, more complex. Okay. Now a little bit more math. So there's you can take two spherical harmonics with the same L, same M, okay, but different angles, theta and phi. In this case, theta dashed and phi dashed, and you can multiply those two harmonics, spherical harmonics, with different angles, and sum them over M, over the whole range of M, which ranges from minus L to L, these integers, okay, and you'll get, the result is that sum is equal to this expression here. So 2L plus 1 over 4 pi times PL of cos alpha. Now I need to explain two things here. This is not PML, this is PL. This is the Legendre polynomial. It is not the associated Legendre polynomial. Right? It's just PL. It's just one parameter here. And this alpha, what's alpha here? Oh, it's got nothing to do with the alpha that we did before in the polynomial. It's perhaps it might have been better to use a different symbol here. But anyway, alpha here is the angle between these two angles. Like it's a bit hard to visualize with a camera, but let's say your angle theta phi gives you a vector in that direction, let's say. And a different two angles, theta dashed and phi dashed, might give you an orientation this way. So that way and that way. So your angle theta here would be the angle between, lying in the plane of these two vectors. So alpha then is the angle between these two orientations, these two vectors. Those two vectors lie in a plane, and that angle alpha is measured in that plane. Right? It's the angle between those two vectors. One vector has its orientation is theta phi, and the second its orientation is theta dash phi dashed. Okay. All right. So that's the end of the appendix. So we've done the appendix. Now we can go back to chapter 7 on angular momentum and push on with the physics, right? So we're done with the math. Now actually these polar plots are actually part of chapter 7, but they were referred to in the appendix, so there's a bit of a mishmash between the two. So, okay. Now, a bit of a comment here. You have your ALE, your associated Legendre equation. There are solutions to it that are not of polynomial form. That they're solutions, and they do not take the form of a weighted sum of powers of x. This is just for your information. The problem is they blow up, become infinite at theta, when theta is 0 and pi. Okay, and physicists hate infinities, so those solutions are rejected. Okay, so just so you know, there are non-polynomial solutions, but they're not accepted in physics because they have these infinite values under these circumstances. All right. Now, what follows here is a bit of repetition in some ways, but it's good revision. You've got what are we talking? Are we talking? Okay, the associated. So this P here